Before any dome, the numbers. Harvard's Joint Center for Housing Studies counts 22.7 million cost-burdened renter households in the United States right now, 12.1 million of them spending over half of what they earn on rent alone. HUD-backed research puts the national housing unit deficit somewhere between 3.8 and 5.5 million units. That is the gap this video is actually about. This is one proposed answer, a 2V geodesic dome. Not a rendering somebody drew to look convincing. Every shape, every strut, every dollar figure in this video was generated by one Python tool set running on the presenter's own machine. That tool set is also the product. By the end, you will have seen the argument for the dome and the software that builds, prices, and explains it. Zoom in, and the whole shell is only 2 parts repeated. 30 short struts, cyan here, and 35 long struts, amber, meeting at 26 hub vertices. 2 lengths. Not 20, not 202. That is the entire structural parts list for a 2V dome. And it is exactly what the simulator's own geometry engine computes, not a marketing simplification. You will sometimes hear that a 2V dome's 2 strut lengths follow the golden ratio. They do not, and this project would rather show you the arithmetic than repeat the claim. Short is 0.546533 of the radius. Long is 0.618034. Divide them, and you get 1.130826. The golden ratio is 1.618. Different number. This project's own teaching tool has made that exact correction since before this video existed. Here is the structural reason 40 of a dome's panels are triangles and not squares. Push sideways on an unbraced square frame and it racks. The corners hinge and the whole shape leans. A triangle cannot do that. Fix all 3 side lengths and the shape is completely determined. There is no hinge left to give. Add 1 diagonal member and the square becomes 2 triangles. The racking disappears because you didn't reinforce the square, you replaced it. A geodesic dome skin is 40 of those triangles already assembled, curving in every direction at once. It is not bracing added to a building. Triangulation is the building. The simulator builds every dome in the same order, station by station. Floor first, then the 65 strut frame you just watch come together. Immediately after the frame, a utility column rises from the floor to the apex, carrying water on one side and power on the other, stages 4 and 5. Rough plumbing and electrical fixtures get stubbed out from that same column at stage 6, before anything closes up. This is this project's specific answer to the oldest objection to curved rooms. Where do the straight line things go? Other designs solve it with a rectangular utility core built against one wall. Different shape, same idea. Put the plumbing and the cabinetry where straight lines belong, and let the dome do only what domes are good at, which is enclosing space. Then the shell claddings up, 1 layer at a time, in the exact order the simulator's own stage list uses. Insulation, interior sheetrock, structural sheathing, a water barrier, shingles, and a fiberglass finish coat. 6 layers, 1 shape. Every one of them has to wrap a curved surface instead of flat one, which is a real fabrication difference from stick framing, and part of why the panel and jig approach later in this video matters so much. Stage 13, a watertight hatch, built the way a boat hatch is built. A raised combing, so water has to climb before it can reach the door, and a locking wheel that seats the door against a gasket instead of trusting a simple latch. Stage 14. The interior fit-out follows the column. Kitchen cabinetry tight against it, bed and bath on the rest of the floor plan. Nothing here waits on a custom curved cabinet. Every straight fixture sits against the one straight core in the room. Stage 15, the last one. Solar, placed only on the faces the dome's own geometry, says face the sun. The same face data that drove the golden ratio correction earlier in this video is what decides where a panel is allowed to go. Then, After all 15 stages, the entire finish shell lifts as one piece from a ring at the apex. In this project's assembly line simulator, that crane sets the dome down on a sun-tracking turntable. It is a manufactured product, handled like one, start to finish. Round 1 is the simplest possible test. A bare shell, no finishes, size so both buildings enclose exactly the same 3,840 cubic feet. Same lumber rate, same skin rate, same labor rate for both. The only variable is the shape. The box costs $12,426. The dome costs $9,444, 24% less, using 55% less framing and 26% less exterior skin to enclose the identical space. Round 2 is harder on the dome, on purpose. Same 640 square foot floor, but now both buildings are fully finished. Kitchen, bath, mechanicals, the works. The dome is only 2.7% cheaper here, not 24%. That smaller number is the trustworthy one. A finished home's cost is dominated by kitchens, bathrooms, and mechanical systems that cost the same no matter what shape the walls are. So shape alone was never going to rewrite the whole budget. The number worth remembering from this round is not the price. It's the volume. For the same footprint and almost the same money, the dome encloses 40% more space, because a hemisphere captures the volume a flat ceiling throws away. That is this project's actual pitch for a finished home. Not that domes are dramatically cheaper. The numbers on screen just showed you they usually are not, but that the same money buys measurably more room. Wind and seismic load spread through this shape differently than through a box. There is no single flat wall for pressure to concentrate on, and load moving through a triangulated lattice has far more paths to travel than load moving through a stud wall. That is a genuine structural property of the geometry. It is also exactly as far as this project is willing to take the claim. A sphere encloses more volume per square foot of skin than a box does, and less skin means less area for heat to cross. That part is just geometry. This project's own insulation model lands at roughly an R41 effective value for a representative build. A 2024 simulation study of geodesic tourist accommodations found 52% lower cooling energy. That is one specific study of one specific building, not a universal law. Anyone who tells you every dome uses 30 to 50% less energy, regardless of climate or how it's built, is overselling the shape. This is Chap's own framing from the source material behind this video, and it's the right one. A 2V dome is not a custom house shaped like a dome. It is a standardized product. Minimal geometry, factory repetition, rapid assembly. 2 strut lengths, 2 triangle shapes, 30 of one, 10 of the other. Every part in a jig. Every part color-coded, the whole shell flat packable. Federal research on modular construction broadly finds schedules compressed 20 to 50% and costs cut up to 20%. That is evidence about modular construction in general, not a guarantee for this specific shape, and this project is not going to blur that line. The same simulator that draws the struts also runs the factory math. One pipeline production line, modeled station by station with the framing stage as the bottleneck, turns out roughly 82 domes a year. At that rate, the line covers its own annual fixed overhead in about 19 units and recovers its full capital cost in about 44. The kind of arithmetic a lender, not a marketer, actually asks for. Set a representative dome from this simulator against this project's own conventional manufactured home benchmark, and it prices 19% lower, uses 57% fewer labor hours, and models 50% fewer build days. Those are this project's own assumptions, stated plainly, so you can disagree with any one of them, not a claim dressed up as a fact. A serious version of this pitch does not pretend the curved wall is free. Cabinets, plumbing runs, and large custom windows all want straight lines and flat planes, and a dome has to earn the right to ignore that. The answer is not to fight the curve everywhere. It's to concentrate the straight lines into one place, this utility core, and let standardized triangular openings handle windows instead of one-off curved glass. And no, a light shell does not mean you skip an engineered foundation. Leaks get solved the way this hatch solves them: gasket joints, a rain screen, and real testing, not an assumption that curved surfaces shed water better. Fire rating comes from non-combustible cladding, the same as any code-compliant building. And the unglamorous stuff? Appraisal, insurance, code officials who have never seen this shape get solved with paperwork done in advance. Engineer-stamped designs, pre-approved plans, lenders and appraisers already lined up. Fannie Mae's own selling guide already allows dome-secured loans when the appraiser has enough information. The work is making sure they do. Before the close, the claims this project deliberately will not make, because overclaiming is what gets a new building type laughed out of a lender's office. A dome is not disaster-proof. It does not always cost less than a normal house. You just watch the honest, smaller number for a finished home. The strut relationship is not the golden ratio. Natural airflow does not eliminate the need for real HVAC design. A kit is not automatically legal because an owner assembled it. And this shape is not the answer for dense urban housing. It never claimed to be. Here is where the case actually holds: starter homes, rural housing, accessory dwelling units, workforce and veteran cottage communities, disaster-resistant low-rise construction, and remote or off-grid sites where shipping a flat-pack shell beats trucking and lumber. That is a narrower claim than domes will replace housing. It is also one this project can actually defend line by line with its own numbers. 4 product tiers, and every price on this panel comes from the same pricing function running inside the interactive simulator: a turnkey off-grid dome home, a storage shed, a greenhouse, and a welded steel plate storm shelter. None of that is invented for this video. It is the actual configuration table the software ships with. Standardized financing is on this project's own list of things that must be solved before any of this scales. So here's a real answer. This representative home dome, 10% down, 11.9% APR over 60 months, comes to about $2,078 a month. That number exists because the software computes it the same way it computes everything else in this video, not because it sounds good. Every model, every number, every camera move in this video came out of the same code base: a dome designer, a factory simulator, a comparison engine, a local voice studio, and this presenter engine, which has spent the last several minutes building its own sales pitch out of nothing but a text script. That is the actual product. The argument for the dome was never separate from the software that proves it. They ship together, and you just watch them work.